In recent lecture A's of our course, we've been looking at nonlinear systems of differential equations, especially something called the competing species model. Here in lecture 32A, that continues. We're going to look at a cooperating species model instead. We're also going to look at two very special kinds of systems, Hamiltonian systems and gradient systems, that have very special functions that go with them, Hamiltonian functions and potential functions. We're going to need technology quite a bit in this lecture. We're going to need Mathematica to help us do the calculations. But the most important thing for my students especially is just understanding the main idea. What is the big picture? We're going to use the technology to help us understand. So let's start with the cooperating species model. It's going to be a nonlinear system, very similar to the competing species model, a very similar kind of form. We've got an unknown parameter mu. dx dt is f of x, y is, well, this term represents logistic growth in the absence of y, plus the interaction term that's got a positive coefficient. So when y is positive, that contributes positively to x's growth rate. Similar kind of thing for y. Logistic model in the absence of x. Carrying capacity for x is 40, carrying capacity for y is mu. That's the unspecified parameter. And again, we have a positive interaction term. These species are cooperating. Mu should be positive for this to make the most sense. However, for the purposes of interest, I'm going to allow mu to be negative because some interesting things happen even when mu is negative in this particular model. Here's the corresponding vector field. And as always, for the purpose of finding equilibrium points and drawing null claims, it's a good idea to factor, if possible. The right-hand side of the dx dt equation has a common factor of x that can be factored out. The right-hand side of the dy dt equation has a common factor of y that can be factored out. That helps us solve for the null claims. And just like before, there are 4 equilibrium points, 2 of which depend on the parameter mu. I would encourage you, if you really have the interest in understanding, to go ahead and pause the video, take the time to check all 4 of these equilibrium points work, especially this last one in the first quadrant, certainly when mu is positive, but even when mu is negative, and not too negative, it will be in the first quadrant, not too far negative. For the purpose of finding the Jacobian matrix to linearize, it's a good idea to expand this out so you can take derivatives. So here's what they look like when you expand them out. And when you take the derivatives, the appropriate partial derivatives, here is the Jacobian matrix. Okay, so you might want to pause that if you're taking notes and write that down, because I'm about to go to the Mathematica now and do our analysis and make our graphs in Mathematica. So here is our right-hand side functions, my f and my g function. G depending on a parameter mu. That's unspecified. I might be interested in bifurcation values of mu. Here I am defining my vector field, capital F. Here's where I can solve for the equilibrium points, and you can see you get x is 0, y is mu, x is 40, y is 0, x is 0, y is 0, that's the origin, and also the more complicated one, x is 48 plus 3/5 mu, and y is 16 plus 6/5 mu. We can compute the Jacobian matrix. This is the general Jacobian matrix. These d's are computing derivatives, appropriate partial derivatives, and ultimately we're plugging in the point x0, y0. Now I can plug in particular equilibrium points and get these Jacobian matrices, and as we've been talking about, we can use these to help linearize with the Hartman-Grobman theorem. For example, the equilibrium point at the origin has a Jacobian matrix when you plug in the origin that is diagonal, and the eigenvalues are on the main diagonal, 40 and mu. So certainly when mu is positive, the origin is a source, a real source. When mu is negative, it's actually a saddle point. And again, we are going to look at the case where mu is slightly negative here, so we will see a saddle point in that case. The other two here and here are upper triangular and lower triangular. The eigenvalues are still on the main diagonal, and you can think about what the values of those eigenvalues as mu changes. They are going to be real numbers, sometimes positive, sometimes negative. So I would encourage you to think about that. At the more complicated equilibrium point, the Jacobian matrix is more complicated. It's better to look at the trace and determinant. Maybe plug in a particular value of mu to find the eigenvalues. For example, when mu is 10, we get 2 negative eigenvalues. So that point is a sink. We could plug in some other value of mu, like mu equals 100. Is it still a sink? Yes, we still have 2 negative eigenvalues. We can also plot this in the trace determinant plane. We can make a plot of the trace and determinant as the parameter mu changes, and as we've talked about with that, the key thing is we're trying to look for where it crosses critical loci, one of which is the horizontal t-axis is crossing right about now. So the system is going to change from a saddle point to a real sink for that fourth equilibrium point at that value mu. I think it's negative 13.3 repeating. Continue letting mu increase. It looks like we stay a real sink after that point when mu is bigger than negative 13.3 repeating. Again, for that fourth equilibrium point. We can make the phase plane, and here is an animation of the phase plane showing what happens as our parameter changes. Here's what it looks like when mu is negative 50. Think about what this means in terms of the species. Like we have the x species. X is its population in the y species. The value of y is its population, perhaps in thousands or millions. And we're seeing from when mu is negative 50, no matter what happens, y dies out. These solutions focusing on the first quadrant here head toward x is 40 and y is 0. Y goes to 0. X comes to a stable equilibrium in the x direction. That is a sink. Let mu continue to increase. We see the y nucline here, which is in pink. That's the y nucline. The brown one is the x nucline, moving upward as mu increases. And we can see the third and fourth equilibrium point coming up, and when mu hits negative 13.3 repeating, which I'm not on here exactly, those two equilibrium points that were there, here and here, merged, and then when mu is bigger than negative 13.3, they separate again. And once we are, even when mu is negative, so it's like you have a negative carrying capacity, y doesn't die off. It goes down, generally speaking, toward a lower value, but it doesn't completely die off. This point that has gone into the first quadrant has become the sink, and this other point down there now has become a saddle point. If mu continues to increase, it's a similar kind of behavior, but now the equilibrium value of the y species gets higher and higher, and for x as well. These are cooperating species, so that makes good sense. If x were absent and mu is big enough, the y model would be a logistic model, and you'd have this point being a sink in that direction. Okay, so a bifurcation occurs evidently at negative 13.3 repeating for mu. And again, this is showing us what's happening, and the Jacobian matrices can tell you what's happening near these equilibrium points as long as the eigenvalues have non-zero real part, as we talked about with the Hartman-Groman theorem in the last lecture, 31a. That's all I want to say about the cooperating species model. I would encourage you to think about it some more. Now we're going to move on to two special kinds of systems, Hamiltonian systems and gradient systems. For my students in the Blanchard, Devaney, and Hall book, these are in both sections 5.3 and 5.4 separately. In the next lecture, 33a, we will talk about some applications, especially of Hamiltonian systems, to physics. But right now we're just talking generalities. We're not going to talk about applications. A Hamiltonian system in the plane. There are Hamiltonian systems in higher dimensions, but as you would expect, they are harder to understand. So let's start with the plane. Takes the following form for some C2 function h. What does C2 mean? That means twice continuously differentiable. These first and second derivatives both exist, and are continuous everywhere in the plane. I'm assuming over the entire plane just to keep things simple. I am abusing notation here. I'm letting the letter h represent two different things, both a dependent variable and a function name. But as we often do in differential equations, we don't let that bother us. Okay? That's called a Hamiltonian function of the system if the system has the following form. dx dt, also called f of xy on the right-hand side, is the partial derivative of the Hamiltonian function with respect to y, the second variable. And dy dt, also called g of xy on the right-hand side, is the opposite, that's no typo there, that negative sign should be there, of the partial derivative of the Hamiltonian function with respect to x. Keep in mind these partial derivatives depend on x and y, thus giving us still an autonomous system of differential equations. Kind of a strange thing. Why in the world would we study such a thing? They do come up a lot in physics, for example, when we have especially problems involving conservation of energy, as we will see. Got some key facts to talk about here, and then we'll look at some examples. Key fact number one. The values of the Hamiltonian function h are conserved, constant, along solution curves, just like conservation of energy. maybe the Hamiltonian function is the energy. The total energy, say, mechanical energy would be kinetic plus potential energy, for example. This can be verified using the multivariable calculus chain rule. Let me give you the basic idea, even if you've not seen the multivariable calculus chain rule before. If we differentiate with respect to time the value of the Hamiltonian function along a solution curve, meaning I need to imagine plugging in, say, a little x of t and a little y of t, where, well, we usually think of these things as column vectors. The column vector x of t, y of t is a solution of the system, of the possibly nonlinear system, okay? Not saying I have a formula for this, and in fact in the more complicated examples we won't be able to find formulas for x of t and y of t, but we can still think abstractly about what this would be. But you need to know the multivariable calculus chain rule. The value of h depends on, first of all, x and y, but then the value of x and y both depend on t. What does the multivariable calculus chain rule say to do? It says find all partial derivatives of upper variables with respect to lower variables. So for example, the derivative of h with respect to x is written with partial derivative notation as dx dh dx with curvy d's. Similar kind of thing for the derivative of h with respect to y. And then the derivative of x and y with respect to t we can write with ordinary derivative notation, regular looking d's, dx dt and dy dt. Once you have written those derivatives down or found them, if you've got an example, to actually now do this derivative, you multiply the derivatives along each path, the product of these two and the product of these two, and then add the results. I'm not proving that here. You can find a proof in most multivariable calculus textbooks. Kind of a weird looking equation. Partial of h with respect to x times dx dt plus partial of h with respect to y times dy dt. That would be what the multivariable calculus chain rule says in this context. Now use the fact that you're assuming that this is a solution. A solution, not any old parametric curve. It's a solution of the system of differential equations. So, for all values of time, dx dt equals this partial derivative if you were plugging in x of t and y of t. So replace dx dt with dh dx. Replace dy dt, oops, that was a mistake, dh dy. Replace dy dt with what it equals, negative dh dx. These two things are the same, they cancel completely. This thing is identically zero. That's supposed to be 3 lines there. Identically zero, always zero. For all time t. Now you don't see any t's in here, so that gets confusing. But realize these things all depend on x and y, and in turn, along a solution curve, all those things depend on t. And we don't even need to know what the formula for the solution curve is. This abstract derivation verifies that the derivative of the values of this function along the solution curve are constant. The values are conserved. And that's helpful, okay? That's not just something to remember. Just like conservation of energy in physics is helpful for solving problems, this is helpful for understanding what's going on. In fact, this is the conclusion. A given solution curve of the system must therefore be on the level curve of the Hamiltonian function h. So if you could draw the level curves of h, then you could draw solutions. And we will, with technology's help, especially. Key fact number 2. Over the plane, which is a nice domain, the system is Hamiltonian if and only if the partial derivative of f with respect to x, the right-hand side of the dx dt equation, is the opposite of the partial derivative of g with respect to y, which g is the right-hand side of the dy dt equation. F does equal this partial, g does equal the negative of that partial. Why is this the case? It's because of the equality of these two things. When h is nice, when h is C2, twice continuously differentiable, something called Clairaut's theorem says that these mixed partial derivatives are equal. And certainly this partial derivative of f with respect to x is equal to this. just differentiate this function with respect to x, and we'd write it symbolically like that. Certainly the opposite of g with respect, the derivative of the g with respect to y, since because of the negative sign there, would be the second order mixed partial that you see there. And again, by this Clairaut's theorem, these are going to be equal when h is a nice function, twice continuously differentiable. Why do we need the plane to be a nice domain? Because it's a technical kind of thing. Let's just suffice it to say that the plane is nice. If you're interested, you can look up what a non-simply connected domain is and how that might affect this. But for us, this is going to be good enough. We will deal with nice examples. So this is a condition to both check to see if a system is Hamiltonian or not. And yeah, both ways. It checks to see whether a given Hamiltonian system, whether a system is Hamiltonian or not. Key fact number 3. Non-degenerate equilibrium points for any Hamiltonian system in the plane. Non-degenerate equilibrium points. Non-degenerate means the linearized system has an eigenvalue that's not 0. When the eigenvalue is 0, weird things can happen. That's what I'm saying down. Ultimately, we'll see that weird things can happen. Not in this lecture. In a later lecture, we'll look at an example. Probably 33a, we'll look at an example where a non-degenerate equilibrium point, something weird happens. But in the non-weird case, the equilibrium points can only be solid points or centers. You might pause and think about why you might think that would be true based on these other observations here. Not sinks or sources of any kind, whether spiral or not. All right, let's look at a couple examples. Here's a quadratic right-hand side Hamiltonian function example. Right there. I'm saying the answer is, it is Hamiltonian, but I'm asking a question first. Is the following system Hamiltonian? If so, find a Hamiltonian function, find an h function, where this is the partial of h with respect to y, and this is the opposite of the partial of h with respect to x. Maybe you can even figure it out right away here. If so, yes, find that function. If not, sketch the phase plane or phase portrait anyway, with Null-Klein's help, for example. Well, what's that condition to see whether this is a Hamiltonian system or not? Take the partial derivative of f with respect to x and see if it equals, I'll put an equals question mark here, the opposite of the partial of g with respect to y. Both of those partial derivatives are always 0, so yes, it definitely happens. These partial derivatives are equal to 0 for all x comma y in the plane. So you could generalize this. If in fact the f function only depends on y and the g function only depends on x, and they're nice functions, a Hamiltonian function will exist. This will be a Hamiltonian system. How do you find the Hamiltonian system, the Hamiltonian function? Integrate. Right? This is supposed to be the partial of h with respect to y. So integrate that with respect to y. What would we get? I'll just write h in abuse notation here. We get h is 1/2 y squared. But wait a minute. How is that going to have a negative derivative of h with respect to x equal to this thing? I don't see any x's over there. Well, when you integrate this to find that, pretend x is constant and add on a constant of integration that depends on x, because x is constant when we do the first integration. You could call it c of x. Our book calls it phi of x, but that's not the same phi we've been using in other applications, where phi of x is an unknown function of x. Now differentiate this with respect to y and also use a minus sign. The negative derivative of this with respect to x, would be negative phi prime of x. I want that to equal, I want to set that equal to the right-hand side here, x minus x squared. So whatever phi of x is, I want the opposite of its derivative to equal x minus x squared. So I need to integrate this and then add a negative sign in there and replace phi of x with that. And if you do that, here's the answer. The phi of x is right here. That would be what you get when you integrate this with respect to x and then put a minus sign in front. You get, with the integral, you get 1/2 x squared minus 1/3 x cubed, but then distribute a minus sign through, and you get 1/3 x cubed minus 1/2 x squared. The combined function now, add on the 1/2 y squared, is a Hamiltonian function for this system, and you can double check that. All right, so what's this phase plane look like? Let's see if we can draw it somewhat by hand, and you saw I have the better pictures on the right here. Let's see how far we can get by hand, and I have to draw it a little bit to the left here, which is going to make it overlap, I think, but the whiteboard doesn't let me go too far to the right there, the smartboard here. Null lines can help. What's the x null line? Where y is 0. Which is the x-axis? The x-axis, come on, right, is its own null line, so to speak. You got to cross the x-axis with vertical tangents. Solutions do. What about the y null line? Where this is 0. That can be factored as x times 1 minus x on the right-hand side there. The y null line consists of two vertical lines at x equals 0 and x equals 1. X equals 0 is the y-axis. Y equals 1 is another line. Stay right about there. Where distinct null lines cross, you get equilibrium points. Again, the x null line is the x-axis. It's crossing these two y null lines at these 2 points. 0, 0, and 1, 0, actually. Then you can think about the sign of these derivatives in these 6 different regions of the plane. When you're above the x null line, where y is positive, the x dt is positive. Motion of solution curves is to the right. And when y is negative, the x dt is negative. So solutions move to the right up here and move to the left down here. What about up-down motion? Think about the sign of this thing. When x is big positively, x minus x squared, this product is going to be negative. Downward motion of solutions. Also, when x is big negatively, you have downward motion of solutions. In between 0 and 1, you have upward motion. So overall, you have southeast motion there, northeast motion there, southeast motion there, southwest motion, northwest motion, southwest motion of solution curves. Let's draw some. Evidently, they look about like this, and there might be some symmetry involved here. Maybe it sort of is like a reflection across the x-axis here, it seems like it might be, and I'm not drawing this very well. Something about like that. Some other curves might go like this. And if you're close enough to this equilibrium point, it should make sense you've got to go around and around. Perhaps it's a periodic solution. And if I said Hamiltonian systems, equilibrium points have to be saddle points or centers. That is going to be a center there. And this point right here is going to be a saddle point. That one right there. Solution's going by like this, by like this, by like that, and by like that. That is a saddle point. And there is one really special solution that approaches the origin as t goes to minus infinity, but also approaches it as t goes to plus infinity. It's called a homoclinic orbit, if you want to look that up. There's also a solution that goes down this way, approaches the origin as t goes to minus infinity, and comes in this way, approaches the origin as t goes to plus infinity. That is a pretty quick picture of the phase portrait in the phase plane. Here is technology's versions, and I'll erase my version. I did it purposely in 2 ways here. This way is the way we've done for the most part so far. Color-coded. Pink represents northeast motion of solution curves. Blue represents northwest motion. Yellow represents southeast motion. Green represents southwest motion. The computer can do a nicer job than I can. And here is a new kind of picture. You see some some curves in there and some shading. Those are the level curves of the Hamiltonian function. Along any one of those curves, say this one right here, the value of the h function is constant. You plug in any point along that curve, you're going to get the same output. Okay, and here's where I got the pictures if you're interested in the code. Now let's do a more complicated example. Well, let's see. Yeah. Let's do a more complicated example now. And let's also sort of go in reverse. In the previous example, we have the system, and we figured out the Hamiltonian function. This time, let's start with the Hamiltonian function and figure out the system. In fact, any nice function can correspond to a Hamiltonian function. I can let h be any nice function. For example, I could pick this function. A fourth degree polynomial in x and y. So I'd have to figure out, for the dx dt equation, the partial of h with respect to y. What would it be? Think about it with me. It'd be negative 8y cubed. That differentiates to 0. Differentiate this with respect to y, you get plus 10x squared. Treat the x as constant. To 0, and then minus 8y. Then the dy dt equation would be the opposite of the partial of this with respect to x, treating the y as constant. Here's the answer. Double check the second one, say. Partial of h with respect to x starts out negative 4x cubed, so I have a positive 4x cubed. Plus 0. Differentiate this with respect to x, you get 20xy, which becomes a negative 20xy because of the negative sign. Minus 10x becomes a plus 10x, and then a 0. There is the corresponding Hamiltonian system. It involves cubic functions on the right-hand sides. Can we reverse engineer the Hamiltonian function? If we started with this, can we figure out h? I will just say yes, I won't do it. And I will say you'd have to do integration, though it would be trickier. You could once again, for example, integrate this first right-hand side with respect to y. I guess I'll go ahead and start it. Integrate with respect to y, you're going to get negative 2y to the fourth, plus treating 10x squared as a constant, 10x squared y, minus integrate negative 8y, you'll get minus 4y squared. But then a constant of integration, which could depend on x. I'll call it phi of x again. Again, different use of phi than we've done before. Then we can take the partial of that with respect to x, put a minus sign through it, and set it equal to this, and solve for phi of x just like before. Notice the negative 2y to the fourth is here. The 10x squared y is here. The negative 4y squared is there. And what's left over just depends on x. That would be the phi of x function. So yes, it can be reverse engineered, but it can be a little tricky. If we wondered, is this Hamiltonian to start with? If we didn't know, Hamiltonian systems are very special. Most systems are not Hamiltonian. If we didn't know, we could use the condition about the partial derivatives of f and g. Does the partial of f with respect to x always equal the opposite of the partial of g with respect to y? What is the partial of f with respect to x? Ignore these things here, focus on these. You're going to get 20x. What is the opposite of the partial of g with respect to y? Differentiate this with respect to y, you get negative 20x. Put a negative sign in front of it, you get 20x. These are equal for all points in the plane, therefore this would be a Hamiltonian system. Using technology, we can find the equilibrium points to be these 5 points. Okay, you could try using your technology to find it. I'll show it to you in Mathematica. What else could we do? We could try using linearization. We could try finding the Jacobian matrix. You can double check it's this. We could try linearizing. But wait a minute. Wouldn't the Hartman-Grobman theorem not apply to the centers? It would apply to the saddle points. For the saddle points for the Jacobian matrix, we'd get 2 real eigenvalues with opposite signs. But what about the center? Would we get purely imaginary eigenvalues? Yes, you would. Real part 0, which means, technically speaking, the Hartman-Grobman theorem cannot be used. However, because of the nature of this two-dimensional Hamiltonian system and the fact that solutions do have to lie in level curves, And level curves, for example, about in the previous example, around the equilibrium point at 1, 0 were circular, not circles, but circular, does mean your solution curves have to be on those curves, and in fact were periodic solutions that were close to that point at 1, 0. So technically speaking, we can still think in terms of linearization, but we can't quite use the Hartman-Grobman theorem. This can be used to classify equilibrium points. Let's use technology to do it, though. Technology really is necessary here. I would not want to do this example without technology. Here's Mathematica code that finds the appropriate derivatives for the Hamiltonian function. Oops, sorry about that. Right there. I can enter the vector field. I can solve for the equilibrium points. I guess I've already entered this stuff. You can see 5 real equilibrium points. I did add this extra comma reals to only get real answers. I can put those points in a list that I call EQ points. And here is the contour map of H. It's kind of looking like an alien there, isn't it? Those are the level curves of the Hamiltonian function. I would not want to try to draw those by hand. It would be very, very difficult to try to draw those by hand. And the corresponding phase plane looks like this. We've got, on the left here, we've got 2 pictures we can scroll back and forth to see. On the left here, we've got the phase plane as we would usually draw it. Brown is the x node line, pink is the y node line. You can notice how the solution curves are crossing, the brown with vertical tangents and the pink with horizontal tangents. You've got the 5 equilibrium points. Visually, it looks like this one, and this one are all centers. You've got oh, I forgot math. It doesn't let me do it on Mathematica. You've got periodic solutions that looks like there. These 2 points are saddle points. You can see solutions passing by here, 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 and here. There would be special solutions, homoclinic orbits, for example. One heading toward this equilibrium point as t goes to minus infinity, and it looks like it's going to go around this equilibrium point before coming back to itself, probably by symmetry of the situation. And if you want a little bit more clarity about that, you can look at the other phase portrait where I've got the Hamiltonian functions level curves in the background. Don't have the one that would go around like that, but it would be there. There would be a level curve curving about like this and coming back to that point, and also over here, curving around like this before coming back to that point. 3 centers and 2 saddles. It gets pretty interesting. What about gradient systems? Special kind of system 2, gradient systems. These gradient systems are, you might call, dual to Hamiltonian systems, or conjugate to them in some way. They are related to each other. I am going to use a different letter for the potential function instead of a Hamiltonian function. I'm going to use the letter V because V is a common letter to use. In Blanchard, Devaney, and Hall's book, I think they use the letter G instead of V for this function. This is called the potential function. It is related to potential energy. That's why it's called a potential function of a system. And the system takes this special form. The right-hand side of the dx dt equation is the partial of v with respect to x, and the right-hand side of the dy dt equation is the partial of v with respect to y. If you know about gradient vectors, this should ring a bell. These are the components of the gradient vector of the function v. No negative signs here. Although, truth be told, some people prefer putting negative signs in both spots, and I'll tell you why here in a few minutes. But we will not. Key fact number 1 about these, the solution curves for this system are orthogonal to, perpendicular to, there's that word orthogonal again, level curves of the potential function. You might call them orthogonal trajectories. Actually, that's probably better to call them orthogonal trajectories with respect to the Hamiltonian system, because they'd be orthogonal to solutions of the corresponding Hamiltonian system, where I treat v as a Hamiltonian function, and the right-hand side of this one would be the partial of v with respect to y, and the right-hand side of this one would be the negative partial of v with respect to x. That would be the corresponding Hamiltonian system using a v instead of an h. But you can certainly make either one. And these different sets of solution curves for the two different systems would be perpendicular, orthogonal, anytime they cross each other. Anytime two distinct solution curves from these two distinct systems cross each other. Key fact number 2, over the plane, in other words, a nice domain, not, well, simply connected domain, again, is the official term for a nice domain here. The system is gradient if and only if there's another partial derivative condition, also based on Clairaut's theorem here in the middle. The fact that these second order mixed partials are equal means if the system is gradient, then the partial of f with respect to y will be equal to the partial g with respect to x. No extra minus sign in there. And also we switched around the x and the y from the Hamiltonian case here. That's your equivalent condition for being a gradient system, for there being a potential function, which you can find by integration, just like before. Key fact number 3, non-degenerate equilibrium points, where the eigenvalues are non-zero, for any gradient system can only be saddle points, real sinks, or real sources. Never centers or spirals, whether spiral sinks or spiral sources. Why would that be? Maybe you'd want to think about that geometrically based on what I've said so far. And then let's look at our examples. These are the dual examples to the Hamiltonian system examples. Remember what the Hamiltonian system example was? It was dx dt was y, and dy dt was x minus x squared. Switch those around, get rid of that minus sign. Now we have dx dt is negative x plus x squared, and dy dt is y. That's a gradient system. You can check the condition. Both of those partial derivatives are always 0. Okay? But we are switching around which one gets differentiated with respect to y and which one gets differentiated with respect to x. Clairaut's theorem is the reason behind this when you're dealing with a simply connected domain like the plane. Using integration, you can find the potential function. Integrate this with respect to x. Not with respect to y, integrate with respect to x. You get this. And is that equal to the Hamiltonian function for the other example? I think the signs were maybe switched around. Maybe I better double check for the x terms. Better double check just to make sure. Oh, no, they weren't. We had positive 1/3 x cubed minus 1/2 x squared there, and we have positive 1/3 x cubed minus 1/2 x squared there. But it is still correct. That is a potential function for this system, and it's the same as the Hamiltonian function was for the Hamiltonian example. The differential equations are different, and the solutions will look different, but it's the same function. The level curves of that same function are still relevant. Solution curves will not lie on them. They will be perpendicular to them when they cross them. Yeah, I won't bother trying to draw this by hand, but here it is. Two versions, the old kind of way and the new kind of way with the level curves in the background. Does this make sense? What's the x null line? Where x is 0 or x is 1. These two vertical brown lines at x equals 0 and x equals 1 are now not y null lines, they are x null lines. You've got straight line solutions on them, in fact. Going up there, going down there, going up here, going down there. And the y null line is where y is 0, which is the x-axis. That's a y null line now instead of an x null line. Straight line solutions along there as well. Thinking about the signs of dx dt and dy dt help you draw the 6 different regions here in the phase plane. I would encourage you to check the signs of dx dt and dy dt in these different regions. Let me briefly say when y is positive, dy dt is positive, solutions go up. When y is negative, below the x-axis, dy dt is negative, so solutions go downward, for example. Here are the level curves of v, which again are the same as the level curves of the Hamiltonian function from the previous example, but now the solutions are not lying on top of those level curves, they are perpendicular to them. Every time one of these blue curves crosses the level curve, for example, right there, there's a right angle to their tangents. That would be what it means for two solutions to curve in a perpendicular or orthogonal way is when their tangents are perpendicular at that point. And that happens no matter where you are. Here, it happens over here. anytime blue curve crosses background level curves of the function v, you are crossing perpendicularly. You still have the same equilibrium points now, but now they're not. It was a saddle in the center before. This is still a saddle, though the solutions look different. This is no longer a center, it's a source. You can get saddles, real sources, or real sinks with these gradient systems. You cannot get centers or spiral sinks or spiral sources. Okay? There's no way you can cross level curves like this in a spiraling kind of way and still be orthogonal to those level curves as you cross them when your system is defined on the entire plane at least. Okay? Pretty cool. These systems, again, are related to each other. They're dual or conjugate to each other, sometimes what this is called. Just like before, given any nice function like this example, we can find the corresponding gradient system. Oops, there's a typo there. That should be gradient system. Gradient system is this. Can we reverse engineer the gradient function? Too much copying and pasting and not changing here. Yes, you can. Through integration, you can once again try to figure out V if you know the system. The equilibrium points are the same as before. Jacobian matrix is different than before, but similar, not in the technical similar sense of linear algebra, but related kind of Jacobian matrix. And you can use to classify equilibrium points and help you draw the phase portrait. Let's look at what Mathematica gives us here, and that will be the end of lecture A for this gradient system. Here's the static picture here that we saw before. And here we could, well, that's the simpler example. Here we can calculate these derivatives, find the equilibrium points just like before, and we can look at the solution curves in the plane. I guess I'm just re-seeing these pictures here and showing you this. I guess you haven't seen this picture yet. So this is the gradient system for the more complicated example. It's phase plane. Now, instead of centers at these 3 points, you've got sinks. You still have saddles at these 2 points. One more thing I should say about this is that with gradient systems like this, notice that solutions are always going from darker to lighter. No matter where you are. Those blue curves that you see are moving from darker regions to lighter regions. Darker regions are where the potential function is lower in value. Lighter regions are where it's higher in value. Solution curves have to go from dark to light because the potential function is increasing along them, because the gradient, if you think of it as a vector, always points in the direction at which the function v in this case increases fastest, in fact. It's because of this that some people prefer thinking of gradient systems with 2 negative signs, because it makes more sense to imagine solutions going downhill, like water running downhill from lighter to darker. And if you put minus signs in front of them instead of the way we did it, then solutions will go from lighter to darker. The potential function will be a negative potential function that will decrease along solution curves in that case. And that is what some people do. Thanks for watching.